Login accepted.
Good afternoon. I'm very happy that you survived till this moment and you came to my presentation. Parallelism, something difficult to pronounce, but even more difficult to implement. And in the times of multi-core processor, this is the only way that we need all to follow. And if I made a survey here and ask you what devices you have in your pockets, in your bags, it would turn out that among our laptops, tablets, mobile phone, there is no single one device that has single core processor. So anyway, we are urged to create our application to be parallel and to use concurrency in their execution. So we make our applications concurrent, either by explicitly creating our code that is delegating tasks in a synchronous manner, or we just utilize some frameworks that gives us concurrency out of the box. And then we experience that our app gets slow. What we do? We increase number of threads. This is like the most obvious way what we can do to speed up our application. But what it may turn out that after bumping the number of threads, our application goes slow down even more. So today I'm going to talk about concurrency in general, investigating specifically topic of threading on application level, and then I will try to answer the question why it may be so that after adding some more threads, our application may slow down. Hello, I'm Krzysztof, and my everyday activities revolves around data engineering, which I'm coding in Scala. However, my today's presentation will be entirely focused on Java, and all the code samples that I will be showing on my slides will be also in Java. And I'm working in pretty fancy Swiss company called Swissborg. And my company has its own product, which is a mobile app for buying and selling cryptocurrencies. But it's not a typical trading application, but it's more like wealth management tool. When you where you send your money, you convert your money to crypto, you put your crypto to yield, and basically every day in passive way, you're earning money out of the interest of your crypto staked in the application. And by the way, we are hiring, so if you are Scala developer or you are Scala developer wannabe, you can scan this QR code, check our current vacancies, and you can apply for the position. And this QR code will be also shown in the last slide of my presentation. So what I'm going to talk about today. So I divide my presentation in 3 topics. The first one I called academics part, because it will be a little bit of revision of the things that you probably learned during your university, but I believe it's still worth to revise some things, some basic things from time to time, because every time you revise, you look at some piece of knowledge with greater experience that you have at the moment, and so you can understand the topic better and maybe conclude some new things that you haven't concluded before. Then I will move to strictly part regarding JVM, and I will be speaking a little bit about threading model in JVM, and also say a few words about thread pools and their implementations in JVM. And this all will prepare ground for the final part, which is a calibration part, when by analyzing example scenarios for threading happening in our application, I will try to give a final good calibration recipe, how to configure our thread pools in the way that we will utilize CPU in efficient way, in most optimal way. So let's start with the first part. Why in all we go for asynchronous computation? There can be a couple of reasons. One of them may be that it may be easier to logically structure our code, and that might be the goal. But in general, the most common and most valid reason is that we go for asynchronousness to just speed up execution and shorten the execution time. And there are basically 2 cases that I would like to separate and to stress that these are different cases when this speed up happens. when we wait in parallel for blocking operations and when we execute in parallel some non-blocking operations. And for the first one, when we wait in parallel, we do not need multi-core environment. We'll still speed up execution of our application when we execute our application on single core, because blocking operations doesn't require CPU. And to clarify it even more, let's look at this graphics. So this black arrow is our main thread, and when we have 3 operations to execute and they are synchronous, and each of them is taking 2 seconds, in total we will wait 6 seconds for the whole thread to finish. But when we decide to spread this execution in 3 separate threads, in 3 asynchronous threads, then we will wait in total for 2 seconds. And yet again, I would like to stress it out that those operations may be CPU intensive, like sorting an array or parsing JSON, but it may be also something blocking, like waiting for data from network or reading data from hard disk drive. And a few more words about what are blocking operations. So I would prefer to call it not blocking operation, but blocking function, or even better, blocking call. Because at some point in our code, there is a call of the function that stops executing at CPU and delegates some operations to other part of our system. So as we see in the examples, it can be reading data from hard disk drive. It can be waiting for data coming from the network, waiting for some stream of bytes coming from standard input, or it can be also sleeping, like the thread just sleeps. So there is nothing to execute on CPU. So thread goes in one of unrunnable states, and so it's kicked off of the core, and it doesn't block resources for other threads to execute. And this is the diagram showing possible states of thread in different operating system environments. So between operating systems, the names may be different, but conceptually, all the operating system that we deal with has this set of semantic states. So after a thread is created, it moves to ready state, and then it's a candidate to being scheduled to CPU core. And so when it's scheduled to CPU core, it goes to running state. And then if it's computing for some time and basically its time elapses, so it needs to make space for another thread, it gets preempted and gets back to ready state, or it may call some blocking function and go to block state, sleeping state, or waiting state. And when it finishes its computation, it's just basically marked as finished. So let's analyze some sample scenario. So let's assume that we have a machine with 4 cores. So we have 4 slots for threads to be executed. And we have a set of threads that are in ready state. That's meaning that's nothing like there's no obstacle for them to be scheduled on CPU and start running. And let's focus specifically on this orange one, and we will see example flow that this orange one will go through. So scheduler out of the ready group of the threads schedules picks up 4 because we have 4 cores and puts them on thread, so that those threads are marked as running. And then they are executing for some time, and scheduler on operating system level decides, okay, it's enough for you, let's make space for another threads, and they are getting kicked off. So in terminology of scheduling, they are preempted from the CPU, and they are moved back to ready state. And then new scheduling happens, and again, next threads are being scheduled to cores. In this case, our orange thread still got selected for the thread. And then execution goes on, and at some point, our thread calls some blocking call. It might be, for example, a system call to operating system to read data from hard disk drive. It may be executing some network communication and waiting for data over the network. So the thread has nothing to execute on CPU, so it's marked as blocked. The slot on the CPU is free, and next thread can be scheduled to this slot, and so computation goes on. After time slice elapses, all the threads got preempted, and then new scheduling is to happen. And because our orange thread is now in blocked state, it's meaning that this orange thread is not a candidate for next scheduling. So it's like out of the pool of ready threads, so only scheduling happens within the pool of the blue ready threads. So the scheduling goes on. In the meantime, our orange thread may become unblocked. So for example, data arrives to the network driver. Network driver executes operating system interruption. Then scheduler being interrupted marks this thread as ready again. And so it's again a candidate for scheduling, for further scheduling. So that's how it goes with threads on operating system level. And one note, this is nothing, all the things that I described now has nothing to do with application code, application level way of thinking. It's entirely happening on the operating system level. So that's it regarding the first part, the academics part. Let's move on to JVM. And let's start with the application to kernel thread mapping. So when you write your code, yeah, especially in Java, you have in Java an object that is thread. So this is a logical representation of thread on application or language level. But underneath, there's also a operating system threads about which I was talking on previous slides. So how the mapping between this logical thread and operating system thread looks like. So there are three typical mappings possibilities. The first one is that we have many language level threads that are mapped to one operating system thread. And in this way, it's application runtime that decides which thread goes next. So there are many logical ones, the one physical one, and basically this physical one is the only one executing, and application decides which one of those logical will be next for executing. And we call this mapping model as green threads. So those logical threads are green, are named green. The second possibility is that we have a one-to-one mapping between language level thread and operating system level thread. And in this way, whenever you create new thread in your application, there is a syscall to operating system to create new native thread. And this is a kind of heavy, but in this way, the scheduling responsibility is delegated entirely to operating system level. The language runtime doesn't decide which task will go next. It's entirely managed by the operating system. And there is third model, which is a mix of those approaches, that we have many logical threads on application level, and we have also many threads on operating system level, and both operating system scheduler schedules and the runtime scheduler schedules which thread will be next for execution. And the question to you, which model is present in Java? Who knows? Second one, yes, middle one, one-to-one. This is the current state in Java. However, I will get back to the slide by the end of my presentation because things will slightly change in Java 19. So we have this one-to-one mapping in Java, and what are consequences out of this? So it's entirely out of JVM scope which logical thread will be next for execution and for how long it will execute. So basically, we have no configuration power to basically affect how the scheduling will go on. However, what we can affect is the number of threads that we are creating, and is the way how we segregate our operations to be scheduled on those threads. And this is quite enough still to manage to calibrate our concurrency in optimal way. And few words about thread pools. So why don't we do threading in this way as I'm showing on the slide? So let's analyze quickly this code. We have 3 lists of integer numbers, and we create 3 threads and each thread is basically executing sorting of those lists. This mysterious call of sort out of null is a totally legitimate call because this indicates that the sorting will happen according to natural order of the numbers. And why we don't do that? Because this is not good code. We do not create threads on demand because, as I said, every logical thread on application in application runtime is mapped to one thread on operating system runtime, and creation of such thread takes time, and it's not negligible time. And also, a thread allocates some memory, and this is also not negligible amount of memory. So we don't follow this way. What we do, we create thread pools. So we do not create threads on demand, but we pre-create some group of threads, and those threads take care of execution of our runnable tasks. So in this picture, we can see 6 green boxes, which are basically our threads, and those threads are picking one by one task from the queue and executing them. And each thread has a big loop that is infinitely going on, and operations in this loop are following. First is taking next task from the queue and then executing it and then repeating the whole operation. And this is on application level. So on application level, we create this thread, and on application level, we maintain this task queue. So the same logic presented in previous slide now converted to the case when we use thread pool is following. So in Java, we have the interface over thread pools is executor service. And here we have an example of usage of executor service that we just 3 times submit some task to executor service. And what is important, when we call the submit thing, there is no new thread created, only the dispatch to queue happens. So threads are running somewhere in JVM, and here we just submit those tasks for the queue, and from this queue, the thread will take the runnable object and execute it. And in Java, we have basically 2 main implementations of executor service, which is thread pool executor coming from Java 5 and fork join pool coming from Java 7. And thread pool executor is basically what I described previously, with one remark that the number of threads in the pool may grow and shrink or may be fixed according to what configuration we pass to our thread pool executor. So when we said that it needs to be fixed, it will be fixed, even in the case that there won't be more tasks to execute, but we can also set some limits that it should be not lower than 2 threads and not bigger than 100 threads, and the thread pool will adapt its size according to the load of the task in its queue. And this implementation has one drawback, because let's imagine we have a lot of short-lived tasks. We have many threads, and it may become soon an obstacle that all those threads takes tasks from the same queue. So there needs to be a synchronization on popping of the tasks. So this may become a bottleneck. So when many threads want next task to be taken, they need to wait for each other, and we end up in a situation which is not optimal because we are wasting CPU time basically for this waiting. So there is a newer implementation of thread pool that came in Java 7 that is called fork join pool. And in this case, each of the threads has its own queue, but it's not normal queue, it's double-ended queue. In short, it's called a deck. And what's special about double-ended queue is that you can take elements from both sides of the queue. So each thread takes elements from the queue tail, as normally queue is used. But when some thread doesn't have any more task in its deck, it can steal task from the back of the queue of other thread. And that's called work stealing algorithm. And this thread pool, this fork join pool, is used by default by JVM. And every time you start JVM, this thread pool is created, fork join pool, and with the size defaulting to number of cores on the machine that you are starting your JVM. And you can access this thread pool by calling this code here, fork join pool dot common pool parentheses. So that's it about JVM. And let's move on to the calibration part. So let's analyze this typical scenario. We have a machine with 4 cores, and so we decide, following the default guidelines, to create thread pool of 4 threads. We have also a task queue, and in this task queue we have 2 types of tasks. One type, those green ones, are blocking tasks, and those orange ones are unblocking tasks. And so we go on, the scheduling happens, our tasks are being scheduled to threads, right? Like threads are taking the task from the queue. And what happens now? Basically, the problem is following that out of those 4 threads that we have, only 2 can execute because only 2 have tasks that can execute on CPU. So the other 2 threads that started executing blocking tasks are kicked out of the processor and moved to blocked state. So we are not fully utilizing the resources that we have on the machine. So one of the solutions might be, let's create more threads then. So we are creating 4 more threads. So those threads are popping tasks from the queue, and they are being scheduled or moved to blocked state. And in this case, we are fine. There are some threads in blocked state not eligible for scheduling, and there are other ones executing on CPU, and it's fine. But it may happen that soon all the tasks that are scheduled to the queue are runnable tasks. So all will be in ready state, and all will be eligible for being scheduled to processor. And in this way, we'll end up in a situation that there will be context switching between those threads. So we have many threads, but more threads than we have CPU cores on the machine. And operating system will preempt, like after time slice intervals, will preempt the currently running threads to the ready state and take threads from ready state to the CPU cores. And this context switching is also costly. It takes time. For processor, is like idling time when we do not use processor resources. So we'd like to avoid such situations. So what we can do, and this is this calibration recipe. We can create 2 separate thread pools. One that will be limited in number of threads and will be dedicated only for non-blocking operations. And here we'll have the number of threads should be the number of cores on the machine. And look that it won't grow, it won't be shrinked, and those threads will be typically executing all the time on CPU cores, and the context switching will be limited because we'll have the number of threads equal to number of cores. And we should have another thread pool that can be unbounded, so it may grow. So in this case, when we have like those 2 orange circles waiting in the queue, it can be a trigger for growing the thread pool and allocating those tasks to some threads. And those threads won't be eligible for scheduling. So those threads won't cause context switching, unnecessary time loss. And in this case, we can better utilize the CPU power. And so I executed some benchmark to test it and prove it that this is a good and optimal way for doing things. So I created 50 arrays of 1,000 numbers, and I was sorting them using different thread pool sizes. So I started off thread pool of 3 cores up to 20 cores. And for each thread pool, I basically sorted those arrays. And we may see that the fluctuation is big. because execution time is affected by many things. There can be GC started in the background. That can be another process running on the operating system, maybe kernel system. So there is no clear line like growing up, but we see the tendency. So when my MacBook was using, I think, maximum 5 threads for JVM. So we see that till the value of 5, the time was decreasing. But when I was creating thread pool bigger, the execution time was slightly growing. So we see the tendency. But still, with those small numbers between 3 and 20, the differences are not that big. When I executed it with thread pools of much bigger numbers, we can see the tendency that is like with bigger numbers, the tendency is clearer. Like it's even quite exponential one. That with bigger number of threads and this context switching happening all the time, you basically run our application much slower. Yeah, so that would be this regarding calibration. And one last thing regarding the slide that I promised to get back to is about application kernel thread mapping. We said that in Java we have this one-to-one mapping. However, there is a project Loom going on, and there is already a beta version of it, that in Java 19, there will be new notion of threads, virtual threads, when basically you will be able to create thread in Java that is purely logical. So creation of virtual thread won't cause operating system to create new native thread, but it will be logically on application level, and Java will assign it to one of the physical threads in runtime. Yep, so that's basically it from my side. It took shorter than I expected. So any feedback in application for my talk is welcomed. Yeah, it's good for me to see how audience perceived my talk. And if you're interested in taking chance and applying for job in Swissborg, here's QR code. So thank you very much.